Hey everyone, this is Dr. Walker. Let's go over the second example from v586 on the integral form of Faraday's law. In this example, we're trying to find the electric field induced by changing magnetic field in a solenoid. Let's go ahead and take a look what we have. We have a long solenoid of radius 2 centimeters, so that's the radius. It is wound with 2,000 turns per meter, so that's little n, right? Little n is the number of turns per length, so that's 2,000 is little n. The current through the solenoid oscillates at 60 hertz. So hertz is a frequency, that's F, with an amplitude of 2 amps. So what it's saying here is that the current is oscillating. And so the 2 amps is going to be the maximum current, which we can call I sub naught or I max. What is the maximum strength of the induced electric field inside the solenoid? So we're going to be looking for the electric field inside the solenoid, so for a distance r is smaller than r. So if we draw our solenoid, then what we want to do is we want to pick a loop that is inside, circle a loop that is inside, and it has a little radius r. It's hard to draw that in there. All right, so how do we apply Faraday's law? Well, the first thing is we need to write down Faraday's law. Line integral E dot ds is equal to negative derivative of the magnetic flux with respect to time. All right, so over here, we know that inside the solenoid that the field is going to be circular, and so it's going to be tangent to our path. So we know that E dot ds is the dot product is going to cancel out. We're just going to have EDS. E is going to come out of the integral because it's constant. And ds is just going to be the circumference of our path that we're taking. So we're just going to have E2 pi r, just like the previous example that we just did. And now on the right-hand side, we need to figure out how to take the derivative of the flux. So we know that the flux is going to be the area, negative derivative of the area times the field. And we know that this is the flux, right, going through this loop here, this little red loop. We know that the area is not changing, but only the field is changing. So it's negative A dB dt. So now we need to find an expression for the field. We know that the field inside a solenoid, I'm going to do this on the side here, the field inside a solenoid is mu naught Ni. The thing here is that the current is oscillating, right? We can't just put 2 amps for the current because the current is oscillating with respect, so it changes as a function of time. We know that when the current oscillates, we can write it as follows. We can write that this I here is equal to the maximum current times sine of omega t, where omega is the angular frequency. This is how we write our sinusoidal function when we have alternating voltage and alternating current that's oscillating in time. All right, so now that we have an expression for B, we know that we have to take the derivative with respect to time. So let me just do that here on the side since I have room here. I'm going to take out the constants, mu naught, n, I naught, and then the derivative of sine omega t is going to be omega cosine of omega t. Alrighty, so now we can go ahead and plug that into here. We're going to have E times 2 pi r is equal to negative A times, and let's put what is the area right? We're looking for the change in flux through this little red loop. What's the area of it? It's going to be pi r squared, since the red loop has a little radius r. And then we're going to plug in all of this here. mu naught n I naught omega cosine of omega t. And we can go ahead and cancel out the r and the pi. So you'll notice that what we end up is exactly the same thing that we got in the last example, where we have e, and then we have the negative r over 2, and all of this was the derivative of the field with respect to time. So the same expression that we got in the last problem. And now what we need to do is we need to figure out, well, the question is asking for not just the field inside at a certain distance r. If so, that would be our answer here. But it's looking for the strength of the maximum strength of the field. So when is this field here going to be a maximum? There's a couple things. So first of all, we know that when this field is a maximum, we can just take the absolute value. We don't need the negative sign. And then when it's a maximum, we know that the cosine function is going to simplify to 1. That's the maximum value here. So let's go ahead and write down what we have left here. Just put this little box here. Let's continue right here. So we're going to have the maximum field is going to be equal to r over 2 mu naught n I naught omega. So we have to realize that, well, the maximum field is going to be when r has its biggest value, and that's going to be right at the radius. That's going to be the maximum value. So we can go ahead and put in for the little r here, we can put the big R, the radius. So let's go ahead and plug in all the numbers. The radius is going to be 2 centimeters or 0.02 divided by 2 mu naught, permeability of 4 space, 4 pi times 10 to the negative 7. N is 2000. And then I naught is 2 amps. And then we have omega. Omega is the angular frequency. Remember, omega is equal to 2 pi f. That's a definition for angular frequency. So we can put 2 pi f, where f is the 60 hertz. So we plug in all of these values. We're going to get a maximum field of 0.019 newtons per coulomb. So it happens to be right when the little r is equal to r. And this is still valid. This equation is definitely valid for this case. Now, even though this question doesn't ask it, I wanted to go do a tiny bit more just because some of the homework may also ask for, well, what if you're looking for the field outside rather than inside? Since we haven't done that yet, I just wanted to show you, we don't have to get numbers out, but just how would you approach r is greater than the radius, right? Which means that you're creating a loop. You're going to go around your loop that is bigger, has a bigger radius than r. So all I want to tell you about the process, right? This red loop that you're going to integrate over on the left-hand side here, it still has a radius r, just like this one. So the left-hand side of Faraday's law is going to be exactly the same, E times 2 pi r. And then the only difference is the right-hand side. When you plug in the area of the loop, it's not the area of the loop, but it's the area through which there's magnetic flux changing. So you cannot put pi r squared for the area. You have to put pi big R squared, right? Because the flux is only changing through where the solenoid is. It's not changing everywhere outside. So that's really the only difference in setting this up, is that the area is going to be pi r squared, and you still can do the derivative of the field with respect to time and plug in the expression and solve for E. But you'll see that the answer will look slightly different because now you're going to have a r squared and an r. This answer will depend, just like the previous answer over here, right? It's going to, before we found the maximum value when we were over here, the field depends on the distance, little r. But outside, it also depends on the radius. Sorry for all the beeps. I forgot to turn off the notifications for all those emails coming in, but I always have emails coming in. It's a very fun time always answering emails, so don't hesitate to always email me. Very happy to answer it.